Definition and symbolic representation of similarity. As we dive into geometry, you'll notice that we often encounter different figures that appear to have the exact same shape, even though they differ in size. Think of a small photograph versus a large poster of that same image. In mathematics, we refer to this specific concept as similarity. Now, it is very important not to confuse this with congruency, which we have studied previously. While congruency implies that two figures are identical in every single way, meaning they have both the same shape and the same size, similarity is a bit more flexible. In similarity, we focus exclusively on the idea that the shape remains constant, regardless of how much the size changes. Welcome, everyone. Today, we are going to begin a new topic, the definition and symbolic representation of similarity. Over the next few slides, we will look at the precise mathematical conditions required to prove that two shapes are truly similar. Understanding the concept of similarity. Now that we have established the basic idea that similarity is about shape rather than size, let's dive into the formal definition. Essentially, we say two geometric figures are similar if one can be transformed into the other simply by uniformly scaling it. This means you are either enlarging or reducing the figure by the same scale factor across the board, without distorting its shape. However, I want to be very clear. When we are working specifically with triangles, we can't just rely on our eyes and say they look the same. To prove similarity mathematically, we must satisfy two very specific conditions. The first requirement is what we call condition 1, the equality of corresponding angles. This means that every angle in the first triangle must have a matching partner in the second triangle that is exactly equal in measure. For example, if we are looking at triangle ABC and triangle DEF, we must be able to state that angle A equals angle D, angle B equals angle E, and angle C equals angle F, as we will see in the next slide. Matching these angles is only half of the story. We also have to look at the relationship between the lengths of the sides. Understanding the concept of similarity, continued. Now that we have established that the corresponding angles must be equal, we must look at the second, and equally important, requirement. Condition 2 is the proportionality of corresponding sides. While the first condition focused on the angles, this condition focuses on the lengths of the sides. For two triangles to be truly similar, the ratios of the lengths of their corresponding sides must be equal. In simpler terms, this means the sides are in the same proportion. If one side is doubled in the second triangle, every other side must also be doubled. To see this mathematically, let's look at the ratio of the sides. We compare the length of side AB to side DE, then side BC to side EF, and finally side CA to side FD. We write this as AB over DE equals BC over EF, which also equals CA over FD. It is vital to remember that meeting just one of these conditions isn't enough. Only if both the equality of angles, which we discussed on the previous slide, and this proportionality of sides are met, can we officially conclude that the two triangles are similar. In our next slide, I will show you the specific mathematical symbol we use to represent this relationship. Symbolic representation. To represent similarity mathematically, we use a specific symbol. The tilde, which looks like a small wavy line written as is similar to. So, if we have triangle ABC and it is similar to triangle DEF, we would write this as triangle ABC is similar to triangle DEF. However, I want to emphasize a very important point here, the importance of vertex correspondence. When you are writing a similarity statement, the order of the vertices is absolutely critical. You cannot just list the letters in any random order. The sequence of letters tells us exactly which vertex of the first triangle corresponds to which vertex of the second triangle. Now that we understand the two mathematical conditions required for similarity, equal angles, and proportional sides, let's look at how we actually write this down in a mathematical statement. As we will see in the next slide, if you change the order of the letters, you are actually changing the mathematical meaning of the statement. So always pay close attention to which angles match up. Symbolic representation, continued. If we write out the statement, delta ABC is similar to delta DEF, this isn't just a random string of letters. It explicitly implies a specific mapping between the two triangles. Specifically, it tells us that vertex A corresponds to vertex D, vertex B corresponds to vertex E, and vertex C corresponds to vertex F. Because of this, we have to be extremely careful with our notation. For instance, writing delta ABC is similar to delta EDF would be mathematically incorrect. Why? Because that notation suggests that vertex A matches with vertex E, which isn't what we've established. The only way that alternative statement would be valid is if the underlying geometry changed. Specifically, if angle A equals angle E, angle B equals angle D, and angle C equals angle F. Now, building on what we just discussed regarding the importance of vertex correspondence, let's look closer at what a similarity statement actually tells us. So, as we move into our real-world example next, always remember, the order of these letters is your roadmap for which parts of the shapes match up. Real-world example, scale models. Now that we have established the mathematical rules for similarity, specifically the equality of angles and the proportionality of sides, let's step away from abstract triangles and look at how this applies in a real-world context. Imagine you are an architect tasked with designing a new building. Before construction begins, you wouldn't just build the full-size structure immediately. Instead, you would create a scale model to visualize the design. Let's look at a specific scenario involving a triangular roof section. In this example, the actual full-sized roof is a large triangle with side lengths of 12 meters, 16 meters, and 20 meters. To represent this, the architect creates a miniature model where the corresponding sides are much smaller: 12 centimeters, 16 centimeters, and 20 centimeters. As we move to the next slide, we are going to analyze these two triangles to see if they truly meet the mathematical definition of similarity we just discussed. Real-world example, scale models continued. Now that we have our scenario, where an architect is comparing a large roof to a small scale model, let's break down how we actually prove these two triangles are similar using a step-by-step analysis. First, in step 1, we need to clearly identify the lengths of all the sides involved. For our actual roof triangle, let's call it delta actual. The side lengths are 12 meters, 16 meters, and 20 meters. For our model roof triangle, which we'll call delta model, the side lengths are 12 centimeters, 16 centimeters, and 20 centimeters. At first glance, the numbers look identical, but we can't compare them yet because the units are different. One is in meters and the other is in centimeters. This brings us to step 2, where we must convert the units so we can check for proportionality. Since 1 meter is equal to 100 centimeters, we multiply our actual roof measurements by 100. This gives us actual side lengths of 1,200 centimeters, 1,600 centimeters, and 2,000 centimeters. Now that everything is in centimeters, we are ready to move on to the next step and calculate the ratios. Real-world example, scale models continued. Now that we have converted our measurements into the same unit in the previous slide, let's move on to step 3, where we calculate the ratios of these corresponding sides to see if they are truly proportional. First, let's take the first side of the actual roof, which is 1,200 centimeters, and divide it by the first side of the model, which is 12 centimeters. This gives us a ratio of 100. Next, we take the second side of the actual roof, 1,600 centimeters, and divide it by the second side of the model, 16 centimeters. Again, we get a ratio of 100. Finally, let's check the third side. 1,200 centimeters divided by 20 centimeters also results in a ratio of 100. This leads us directly to step 4, our conclusion. Because the ratio of the first side over the second side over the third side, and the third side over the first side are all exactly equal to 100, we have proven proportionality. Furthermore, since the angles are preserved in any scale model, we can confidently state that the model triangle is mathematically similar to the actual roof triangle. This demonstrates perfectly how the concept of similarity works in a practical, real-world application. Common mistakes to avoid. First, please be careful not to confuse similarity with congruency. I often see students accidentally using the congruency symbol, which is an equal sign with a small tilde on top, instead of the similarity symbol, which is just the tilde itself. It is vital to remember this distinction. While all congruent triangles are technically similar because they share the same shape, not all similar triangles are congruent because their sizes might be different. Second, watch your vertex ordering. This is a mistake that can invalidate your entire mathematical statement. As we discussed in the previous slides, the order of the letters tells us exactly which corner matches which. You cannot simply write, triangle ABC is similar to triangle DEF. If, in reality, angle A matches angle E, you must always double-check your angle equalities before writing down your symbolic statement to ensure the sequence of letters is accurate. Finally, do not ignore the order of your ratios. When you are demonstrating that the sides are proportional, you must maintain a consistent pattern. If you begin your fraction with the side from the first triangle in the numerator and the side from the second triangle in the denominator, for example, side AB over DE, then you must continue that exact same pattern for the remaining sides. It should look like AB over DI equals BC over EF, which equals AC over DF. Keeping this consistency is key to a correct proof. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept of similarity, it is very easy to lose marks on exams by making these 3 specific mistakes. Once you master these details, you'll be well prepared for our final summary. Key takeaways. First, remember the fundamental definition. Similarity simply means that 2 figures have the exact same shape, even if they are not the same size. Think back to our discussion on congruency. While congruency requires both shape and size to be identical, similarity focuses only on that constant shape. Second, it is crucial to remember that similarity isn't just a visual guess. For 2 triangles to be mathematically similar, 2 specific conditions must be met. The corresponding angles must be equal, and the corresponding sides must be proportional, meaning they all share the same ratio. Third, when you are writing your proofs or answers, use the correct mathematical notation. We use the tilde symbol, which looks like a small wavy line, to represent similarity. Finally, never overlook the importance of vertex correspondence. When you write a similarity statement, such as delta ABC is similar to delta DEF, the order of those letters is mandatory. The sequence tells us exactly which vertex matches with which, such as vertex A corresponding to vertex D, as we discussed earlier. Changing this order without a mathematical reason would make your statement incorrect. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways from today's session to ensure everything is clear. Keep these points in mind as you practice your geometry problems. Great job today!